Well, good afternoon, ladies and gentlemen. Thanks for joining us in the Star Theater this afternoon. I'm your Viking resident astronomer, Jonathan Ward. Happy to have you with me this afternoon. I know we're competing with the beautiful weather in lovely downtown Oslo today, and so I'm very honored and grateful that you're here to join me today. I'm going to give you a heads up on a special opportunity at the end of the presentation today. We do have one of the best kept secrets on the ship, which is the Explorer's Dome, a planetarium on the 8th floor of Deck 8 at forward end of the ship, right above the Explorer's Lounge. And I have two shows that I'm going to be doing later this afternoon, and I'll tell you a little bit about those and opening that up to people who would like to come up and see those shows this afternoon. I'll also be doing the same shows during the Sea Day in a couple of days. Before I get into the start of my talk about the history of the universe, I wanted to point out this picture for you here, this video. This is not just a screensaver. This is actual data. This is the distribution of several 100 million galaxies that we have seen so far from Earth, plotting their position in space in 3D. This is how the galaxies are distributed through the universe. And this is probably less than 1/10 of 1% of the galaxies out there. It's just something to give you a little taste of the scope and scale of what we're looking at today. So we're going to be talking about, where did the universe come from? Where are we now in the life cycle of the universe? Where might we be going? And as I started off the other day with my talk about the history of astronomy, we struggle to try to comprehend what we see around us. And so this is an explanation for how the universe began. The first world to exist was Muspel, which was a place of light and heat whose flames are so hot that those who are not native to that land cannot endure it. Beyond Muspel lay the great and yawning void named Ginnungagap, and beyond Ginnungagap lay the dark, cold realm of Niflheim. Ice, frost, wind, rain, and heavy cold emanated from Niflheim, and they met in Ginnungagap with the soft air, heat, light, and from Muspel. Where the heat and the cold met appeared these thawing drops, and this running fluid grew into a giant frost ogre named Ymir. And when he slept, his sweat created the frost ogres. Now, thawing frost became a cow called Athumlia. 4 rivers of milk ran from the cow, and she fed Ymir. The cow was licking salty ice blocks, and after 1 day of licking, she freed a man's hair from the ice, and after 2 days, the man's head appeared. On the 3rd day, the whole man was there, and his name was Buri, and he was tall, strong, and handsome. Buri begot a son named Bor, and Bor married Bestla, the daughter of a giant. Bor and Bestla had 3 sons. Odin was the first, Vili was the second, and Ve was the third. Odin, Vili, and Ve resented the brutality of the giant Ymir, and together they killed him. The sons of Bor carried Ymir to the middle of Ginnungagap and made the world from him. From his blood they made the sea and the lakes. From his flesh they made the earth. From his hair they made the trees. And from his bones they made the mountains. They made rocks and pebbles from his teeth and jaws and those bones that were broken. From his skull the sons of Bor made the sky, and they set it over the earth with its 4 sides, and under each corner they put a dwarf, whose names were East, West, North, and South. The sons of Bor flung Ymir's brains into the air, and they became the clouds. And then they took the sparks and the burning embers that were flying around after they'd been blown out of Muspel, and they placed them in the midst of Ginnungagap. These gave light to heaven above and the earth beneath, and to the stars they gave appointed places and paths. And so, ladies and gentlemen, that's where the earth, the sky, and the stars come from. Or, if you prefer another explanation to explain what we see, in the beginning, the universe was created. This has made a lot of people very angry and has been widely regarded as a bad move. This is from Douglas Adams' The Hitchhiker's Guide to the Galaxy. Or we might choose a different way of explaining where the universe came from. The Egyptians saw the sky goddess Hathor stretching from horizon to horizon, and you can see the stars along Hathor, and this explains, of course, how the Milky Way stretches from horizon to horizon. So the question of where we came from is probably as old as our consciousness. It's the science of cosmology. It's our attempt to grasp the immenseness of the universe that we observe and our place within it. So, we're looking here at the Milky Way stretching from horizon to horizon, and until the 1920s, we thought this was the entirety of the universe. It was only about 100 years ago that we thought this was the entirety of the universe. All the stars of the universe were in the Milky Way. We saw those stars, and we noticed some interesting things that were called nebulas. These had been discovered in the late 1700s. And there were different types of nebulas. We had these gaseous nebulas. This is a picture I took of the Orion Nebula or the Lagoon Nebula in Sagittarius, or we have the lovely Helix Nebula and the Crab Nebula. And then we discovered there were some other types of nebulas that Charles Messier, who had discovered these, said he called them nebulas without stars. And as we developed stronger telescopes and photographic film, we started to see, yes, in fact, there were some stars in these nebulas, and they had these interesting spiral shapes. And it was after the invention of spectroscopy and photography, and we started studying what these things were made out of by taking the spectrographs of these, that we realized that these two spiral nebula type of things here were very different than the gaseous nebula that we saw over there. Edwin Hubble was the one who started looking at these things and examining their spectra, and what he discovered was really shocking. I talked a little bit about redshift the other day, and redshift is what we call the Doppler effect. If you think about the sound that a siren makes when an ambulance is coming towards you, the sound gets higher and then it gets lower. It goes dee 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 dee. That's the redshift in sound. There's a similar type of thing that happens in light. I talked about these lines that are associated with different elements, and what we've seen in some stars is that those lines are shifted a little bit over towards the red side of the spectrum. But when Hubble was taking spectra of galaxies, he found out that these things were not only shifted a little bit, they were shifted a lot. And the smaller and dimmer that these galaxies appeared to be, or these spiral nebulae appeared to be, the farther these redshift lines were going. And so the amount of this redshift that happens is a function of how fast this is moving relative to the speed of light. And so what he's seeing here is that the more distant these galaxies are, the faster they are moving away from us. So not only were these things not local to us, not within the Milky Way, they were far away and immensely far away. And the farther away they were, the faster they seemed to be going away from us. It was a totally mind-blowing experience for him. Now, using this kind of data, there were three scientists back in the early part of the 20th century who really started coming up with the idea of an expanding universe. And the first was a Russian astronomer, Alexander Friedmann, who came up with the idea of an expanding universe in 1922. And he corresponded with Einstein, and Einstein said, I don't think this makes any sense at all, even though Friedmann was using Einstein's equations. Hubble we talked about briefly, and then there was a Belgian priest named Georges Lemaitre who independently hypothesized that the universe was a constant mass and a growing radius to explain the correlation of what he saw between redshift and distance. He published it in a journal in French. It was a Belgian journal and was not widely read in the United States, and so Hubble actually published the same type of information independently derived, and he got the credit for discovering the expansion of the universe. Eventually, now, just 4 years ago, we've now brought Lemaitre into this for his hypothesis, and we call it the Hubble-Lemaitre law now. But this was, again, a correlation directly between how fast something is moving away from us and how far away it is. Now, Lemaitre had a really interesting idea, too. Not only did he discover, did he think about the universe expanding, but he started thinking about what happens if you take this backwards. If you think about the galaxies moving far away from each other, what happens if you go back in time and the galaxies get closer and closer and closer? And he came up with this idea of there being a day with no yesterdays. There was some day that had to have been the beginning of time, at which point these galaxies were all infinitely close together into what he called a primeval atom. And so this he thought was a really kind of elegant theory. What he really liked about it was that, he was a priest. He said you could look at this idea of some sort of primeval atom that expands later on. He said you can either believe this religiously or scientifically. They can coexist perfectly well as far as he was concerned. So he was the one who kind of came up with the idea that something started from the very beginning and started moving outward. And this was derisively called the Big Bang, as I mentioned earlier in my other talk. It's not really a bang, but at some point, out of nothing came everything there was. So I get asked a lot of questions about what is the Big Bang? What existed before the Big Bang? This is one of the first questions I get. Where in the universe did the Big Bang occur? Are we at the center of the universe because everything seems to be moving away from us? What triggered the Big Bang? Or what made that singularity that expanded into everything there is? Or what is the universe inside of? What are we expanding out into? These are some very logical questions that come out of the idea of this expanding universe. And the problem we have is we go back to T0, this is the very instant of everything began. Current physics doesn't make any sense at that point. When you're dealing with infinitely small things, physics just completely breaks down. So none of these questions actually make any sense. So some of the things that you have to wrap your mind around when you're thinking about the history of the universe is that space and time themselves, space-time as a unified thing, was actually created in the Big Bang. There was no before. Nothing existed before the Big Bang because there was no before. There was no concept of time because time and space came into existence at the Big Bang. Now, this is something that is still being debated right now. We're not sure whether there was something going on called inflation, when I'll talk a little bit more about that, where space and time itself is expanding, and then something happened that caused some sort of matter to appear in this inflating universe, which then expanded and caused what we're observing today. So there's still a debate between was there a Big Bang or was there inflation that then somehow matter started expanding into. This one is pretty central, though, is that the Big Bang occurred everywhere in the universe at the same instant. There is no center of expansion. Everywhere we are in the universe was all created at the same time, and we're all moving away from each other at the same way. One way to think about it is thinking about some batter, of raisin batter to make bread. As you bake that, the raisins all move away from each other, so you can't really look at any of those raisins and say one of them is at the center. Well, you could because you have a finite kind of thing, but they all appear to be moving away from each other. We don't know what caused the universe to come into existence. We have no way of figuring that out right now. I get asked a lot about parallel universes, and if there are other ones, we have no way to detect those at the present moment. Someone was asking me the other day, there's a hypothesis about we've got one universe running forward in time and one universe running backward in time. It's a really cool idea, but there's no way to check that out experimentally. So I want to talk a little bit about, if we do accept the fact that if we accept the idea that there was a Big Bang, one of the things about science is that we never say this is the absolute truth. We say this is what we think now, given the information that we have, subject to change as we learn more. But our current thoughts about what happened at the very beginning is, I'm going to unfortunately have to use a lot of words at the very beginning of this because there's no way to put this into pictures. But if you think about the very smallest possible fraction of a second after the Big Bang happened, so 10 to the minus 32 seconds, that's a decimal point with 32 zeros after it and then a 1. So think about that, how small of a second that is, to 10 to the minus 12th, which is a trillionth of a second. That space itself was expanding by a factor of 10 to the 26th, so that's 10 with 26 zeros behind it. Again, it's really hard to kind of wrap your mind around this, but in a trillionth of a second, space had expanded this tremendous amount. We saw, as all of this matter started coming out of the Big Bang, and when I say matter at this point, we're just talking about quarks, the very basic building blocks of matter, that there were ripples that were appearing in here from minor fluctuations in how these quarks were distributed. And so after a trillionth of a second, the universe was already 300 light seconds in diameter, so this is already about the size of the orbit of Venus. So in just a trillionth of a second, going from nothingness to the size of the orbit of Venus in a very, very fast inflation type of thing here. So again, we're not talking about stuff expanding out into space, we're talking about space itself expanding to that size. And so what happens, again, at that point, it's really hard to say that physics existed before that. And now, starting at about a trillionth of a second after the Big Bang, the laws of physics start to make sense. The strong, the weak, the electromagnetic forces freeze out into what we observe nowadays. This plasma of quark and gluon, quarks, again, the basic building material of all matter, and gluons are the things that hypothetically hold quarks together. And that started cooling enough for hadrons to form. So in other words, this is where we start seeing protons and neutrons begin to form with each other. This is the third one is another thing that's hard for us to explain right now. When we look out into the universe, we see matter, we don't see antimatter. And hypothetically, when the universe was created, there should have been equal amounts of matter and antimatter. And if you remember from Star Trek, when matter and antimatter collide with each other, they both eliminate each other and create a tremendous amount of energy. So if there was an equal amount of matter and antimatter when the universe was very small, it should have completely obliterated everything. And so we think there might have been some very minor difference in the amount of matter and antimatter that there was. The equal amounts of matter and antimatter eliminated each other, but there was a small residue of matter that was left over, which is what we see today as the matter in the universe. And so now, by 1 second after the Big Bang, the universe is now 10 light years in radius. So that's farther now than the star Sirius. So in 1 second, we've gone from nothing to farther out, or more than twice as far as Alpha Centauri. So physics has begun now, and now we start creating, we have protons and neutrons coming together to form the first atomic nuclei. We have hydrogen and helium-4, and there are different types of combinations of protons and neutrons coming together. The temperature is still way too high for electrons to be able to bind to those nuclei. And so the universe is basically opaque at this point. Whatever light is going through here is basically being completely absorbed by these atomic nuclei that are around there. So we can't see what was going on at this point in the universe in the first 1,000 seconds. But eventually, by the time we get to about 18,000 years, the universe has cooled enough to allow electrons and nuclei to form the first atoms. And the universe has become transparent, meaning that light can now travel in the universe. Photons can move without running into other atoms or running into atoms and being absorbed. And so when I talked about the cosmic microwave radiation background the other day, microwave background radiation the other day, this is where the photons from the very beginning of the universe that we see started, from about 380,000 years ago. And at this point now already the universe is 40 to 50 million light years in diameter. So this is the evidence we see of the Big Bang. This is radiation that's pretty much uniformly distributed across the sky. The differences in color here represent the difference in temperature of only millionths of a degree above absolute zero. So the overall average temperature is about 3 degrees above absolute zero, which is what we would expect from this happening that long ago. And this is actual observational evidence, and we're getting better and better at refining how how we have areas where there is higher temperature and lower temperature and what that actually meant. So the universe is continuing to expand. We've got the nuclei forming, and now we reach a point what we call the dark ages. As eventually as the atoms, or excuse me, the nuclei have moved far enough apart, they reach a low energy state, and so there's nothing emitting light at all. There's nothing changing energy states to emit photons. So we have this period of about 150 million years where there's no light coming from the universe at all. Whatever was going on back then is kind of invisible to us now because everything's been trapped by neutral hydrogen. And so if you see this model of the universe here, we have the dark ages after the Big Bang, and then eventually what happened is that molecules began forming. And we had the first molecule, which was a surprise to me when I learned about this, was helium hydride, because I always learned that helium as a noble gas is not something that can bind with anything else. But at the energies we're talking about in the early universe, helium could bind with a hydrogen ion. And so this was the first molecule, and we've actually detected that. This was hypothetical, and now we've actually detected this in some supernova explosions. So the universe was so hot that even molecular hydrogen couldn't exist. But after it cooled down, hydrogen atoms could start interacting with this and form molecular hydrogen. And so now what we've done is actually kind of created chemistry. Chemistry has come out of physics at this point. And so we've started, we've got enough energy to ionize molecules, and now photons start getting emitted again. And gravity is causing pockets of density where there's locally dense areas of matter. These things start collecting together and eventually start forming the first stars, which we call population 3 stars. These are hypothetical. We've never observed these yet, but these would be stars that are very massive, 10 to 100 times bigger than the sun, extremely hot, made entirely of hydrogen and helium. No other elements existed at that point. It was only hydrogen and helium. And so we think the James Webb Telescope might be able to see some of these. We just saw, I don't know how many of you saw the news article a couple weeks ago that Hubble had seen the oldest star in the universe so far, and that's still probably not a population 3 star. The population 2 stars formed after these population 3 stars. They lived very short lives. They exploded. They created heavier elements. Those heavier elements, like lithium and carbon and oxygen, came together and with hydrogen and helium and formed population 2 stars. And when those stars exploded, they created even more heavy elements. Like then we start getting into silicon and iron and other things like that. But it was as a result of stars exploding is where the heavier elements were formed. And you go back to that saying that we are made of star stuff that Carl Sagan said. We're actually made of stuff that came from the center of these stars that exploded after they burned out. And we start forming some what we call proto-galaxies, which are the early amalgamations of stars that form along these ripples in space-time. And we'll talk a little bit about how that structure looks. And this is where we think dark matter starts to come into play here. Dark matter is something that we've never directly observed. We've observed its effect, and this was actually kind of hypothesized back in the 1930s, that somebody was observing that galaxies appeared to be moving too fast in clusters to be explained by just the matter that we could observe. So there had to be some sort of dark matter that was still gravitationally affecting these things. So we still don't know what dark matter is. We've never been able to actually detect it. And there are theories that say we can get away with explaining what we see without having to invoke the presence of dark matter. But for right now, we think that's what's happening out there, that there is this dark matter that interacts with things only by gravity. It otherwise doesn't interact with regular matter. So at this point now, we're not 100% sure if the expansion of the universe slowed down. We still don't really know what caused inflation, what drove inflation, how long it lasted. Does it speed up? Does it slow down? And this is something, again, we call dark energy, which is another thing that we've never directly observed, but we think it's the predominant energy in the predominant amount of energy in the universe is this dark energy, which is causing space and time to expand. But we think it may be at this point that the influence of dark matter was enough, the gravity was enough to slow down inflation. We're still trying to figure that out. When I talk about ripples in space and time, this is kind of what we saw is as these interactions were going on, as local areas began to expand, you form these big bubbles. And if you think about how soap bubbles stick together, you've got these membranes between the bubbles. And so what we're actually having here is that these bubbles in the ancient universe, where they interacted with each other, created these filaments or kind of like the walls of the bubble sticking together. And that's where the galaxies hang out. The galaxies all kind of live where the edges of these bubbles are or where the intersections of the bubbles are. That's where we get these clusters, is where multiple of these bubbles come together. So we see the structure of the universe right now is that we have galaxies that are kind of in in these kind of shape, what we call filaments or walls with large voids of empty space in between them. And so as those oscillations died down, the universe just continued to expand, and the matter that we saw very early on now has kind of coalesced into stars and galaxies. So now we think, as we've gotten 500 million to the current age now, that the galaxies that we know about have started to form. Galaxies attract each other gravitationally. So when I talk about the expansion of the universe, what's happening is that the local clusters of galaxies, the places on the walls of those bubbles, or where the bubbles interact together, those form clusters of galaxies, and those are still close enough together that their gravity attracts them to each other. And so when that happens, it creates a new type of galaxy, and it triggers star formation. What's actually expanding is the space in between those filaments. But this is now when the current generation of stars was formed, like our sun. And this is kind of an artist's depiction of what the early universe might have looked like, with all of these star-forming galaxies forming. Talking with James Mather, who's the principal scientist behind the the James Webb Space Telescope, thinks that we might be able to actually see these galaxies with the James Webb Space Telescope. Hubble can't see them because they're too far shifted into the red spectrum for Hubble to be able to observe it, but James Webb might be able to see these. So this is kind of an artist's conception of what the early universe must have looked like. It must have been a sky alive with all of this starbirth that was going on. And to take a very quick detour, several people have asked me, what's James Webb going to see relative to what Hubble could see? And I just wanted to share with you, this is an image that just came out last week. These are the two previous space telescopes, infrared space telescopes, the WISE telescope and the Spitzer telescope. This is the same star field, and then this is one of the calibration photos from James Webb. So you can see how much better our view of the universe is getting with James Webb out there. This is still just test data. This is not even their scientific observation, but this is to give you a clue how exciting it's going to be to see what comes out of the James Webb Space Telescope. And so, this Webb is going to help us see farther and farther back into the distant universe. And I wanted to take one more detour, which is something that I like to call what I like to do with my telescope, which is stupid astronomer tricks. But I like to try to go beyond taking pretty pictures of nebulas, but actually try to see how far I can see, or what other types of things I can see. So this is an image that I took of a galaxy cluster called the Hercules cluster Abel 2199. And you can see some of these fuzzy blobs on here are galaxies. These are galaxies that are about 500 million light years away. So it's taken the light from these galaxies 500 million years to get to us. And it looks like, a couple of these fuzzy blobs and then a bunch of background stars. But I ran this through there's some great programs you can run images through. I ran this through an analysis program. Oops, let me go back to this. Every one of these circles on here, this is a galaxy. So that image has got all of these galaxies in it, and these are just the brightest ones of those galaxies. So I was really kind of blown away that I had been able to see all of these galaxies. There are thousands of them. There's about 300 of them in this picture. And this is just with my backyard telescope. Okay, this is about a 1 hour exposure, but you start to see what's out there. And then zooming in on this brightest galaxy here, I went through and saw that you can actually see there's some quasars on here. This really freaked me out, that I could see a quasar that was 9.5 billion light years away with my backyard telescope. So that QSO, 9.4 billion light years away, I'm looking back 2/3 of the lifetime of the universe back to that thing. That thing formed when the universe was only 1/3 of its current age. So again, gives you kind of a feel for what is out there, and just the immensity of what's surrounding us. Anyway, back to the history and fate of the universe. So I talked about the galaxies forming, population 1 stars forming like our sun. The shape of the universe has crystallized into these filaments and sheets and walls. When I talk about the voids, this is the Laniakea supercluster that our galaxy is part of. It's a supercluster of galaxies, and you can see that they're not evenly distributed. They are kind of clustered together. And you have these huge areas of almost nothingness in between there. And those are galactic voids, intergalactic voids, which were discovered in 1978. The immensity of these things is hard to explain, and it's actually the expansion of these voids which is causing the expansion of the universe that we see. If our galaxy or our sun had been in the middle of one of these voids, we might not have known there was anything else in the universe until the 1940s or so, when we finally got strong enough telescopes to do it. It'd be like trying to see the lights of Los Angeles from Hawaii, to give you an idea how immense these voids are. But you end up with this kind of structure, these filaments of galaxies, and this is the underlying structure of the universe that we know of today. So you've probably got dark matter that's causing the galaxies to cluster together in these filaments, and then you've got the big voids in between them. The voids continue to expand. The galaxies kind of move together in those superclusters. So, now getting closer to the present age now, we think that dark energy has kind of taken hold again. As the universe has expanded, gravity has become a little less important, and the universal expansion has probably started accelerating again. We're not 100% sure. Our sun formed about 9 billion years, 9.25 billion years after the Big Bang. After 10 million years after the sun had formed, it had planets, including Earth. And at 10.4 billion years after the Big Bang, we saw the first fossil traces of life on Earth. So now chemistry has begotten biology. Chemistry has become biology. Biology, somebody said, is chemistry with intention. And so now you have chemistry that tries to perpetuate itself. So we've gone from physics to chemistry to biology. So that's where we are right now. The universe continues to expand. We're not sure exactly how, why, or how fast. But what's the future look like to us now? If if things keep going the way they are, what's going to happen to us? The answer is we don't know. And so I wanted to talk a little bit about some of the theories about what might be lying beyond for us. So our models of the expansion of the universe are obviously missing something, which I'll explain here. There's some really fundamental things that we don't understand about how the universe works. First is to try to understand, how do we know how far away these galaxies are, and how do we know when the universe began? And so what we need to do is determine what the value of the Hubble constant is. The Hubble constant is the direct relationship between how far away something is and how fast it's moving away from us. So there are a couple of different ways of measuring that, which are all very scientifically valid. And first I want to talk about what we call the cosmic ladder method. And this one uses a certain type of variable stars. There are stars that vary in brightness in a regular pattern, and this is called a Cepheid variable, and we figured out there's a very direct correlation between how bright that variable star is and its period of variation. And so some of those are close enough that we can actually see them moving against the background sky, so we know exactly how far away those are. We can see more of these farther away in the Milky Way, and we start getting an idea how big the Milky Way is by how bright those stars are. Obviously, they get dimmer as they get farther and farther away from us. And we can see those same types of variable stars in other galaxies like the Andromeda galaxy, which are relatively close to us. So again, figuring out how bright that star is and how much it's been dimmed by distance, we have a pretty direct measure of how far away the Andromeda galaxy is, 2.5 million light years away. And now there's another type of pretty regular type of star situation called a type 1a supernova. And we don't see those so much. They're pretty rare in our own galaxy, but we've seen them in other galaxies where we've also seen the Cepheid variable stars. And just like Cepheid variables, the type 1a supernova are all the same brightness. We know exactly how far away they are based on the explosion. So even in galaxies where we can't see the variable stars, we can see those supernovas and figure out how far away they are. And so that gives us an idea. We can see those supernova a long way away, and so we get an idea for how far away those galaxies are, as far out as we can start detecting them. And so doing this, we come up with a value of the Hubble constant, and there's not going to be a quiz on this, but we get roughly 73 kilometers per second per megaparsec, which means for every 3 million light years away a galaxy is, it's moving 73 kilometers per second faster. So the farther away it gets from us, the faster away it's moving. So we come up with this pretty precise measurement. We've been able to refine this measurement very, very tightly over the last couple of years, last 20 years. Another thing we've been able to do now is to take this cosmic microwave background radiation and start measuring it and those bubbles that it created. And so by studying that, we come up with a value for the Hubble constant of 68.7. Again, plus or minus 1.3 here. So we've gotten pretty precise about measuring the age of the universe and the expansion rate using these background fluctuations. So we feel very confident about that. What happens is, so if you're using the Cepheid variable method, the distance ladder method, you get this upper bar here that we've come up with a number of 74 or so, and that error bar is getting smaller and smaller. If we use the cosmic background radiation, we come up with 67, and that error rate is getting smaller and smaller. So as the numbers are saying, this is the right number and this is the right number, and they're farther apart, and there's no way to reconcile those two. And then there's a third method, which we're still developing, and that comes up with something that's in between those two. So what does that mean? It means that either the universe is precisely 14.4 billion years old, or the universe is precisely 13.77 billion years old, or something in between. So again, obviously we're missing something here. We feel very confident that all of those methods are scientifically valid, and we don't understand why they come up with different numbers. So does that mean that inflation is increasing or decreasing? And if so, why is that happening? Or is dark matter acting differently than we think it might act? Or the effects of dark energy increasing somehow? Or is there some sort of matter that we haven't detected yet? Or was another period of inflation, was there inflation somewhere in between the initial inflation and where we are now that we haven't detected yet? Or is there just some sort of underlying fundamental property of the universe that we just don't understand? And unfortunately, we don't know what the answer to that is. And kind of the so what in this is, it helps us, if we know that the universe is going to be expanding at a slower rate of speed, then things are probably going to stay together for a longer period of time. If the rate of expansion of the actual space and time is accelerating, then we reach this situation called the Big Rip here. And this is one scenario that if dark energy is taken over at the rate we see now, if it starts to accelerate, in this scenario, the first galaxies will start to get separated from each other about 200 million years before the Big Rip occurs. About 60 million years before that time, the galaxies begin to disintegrate themselves as stars start flying apart from the other galaxies. Gravity is too weak now to hold against the expansion and the inflation of the universe. Planetary systems like the solar system start to become unbound about 3 months before the Big Rip, so the planets start flying away from the sun. And then in the last minute, the stars and planets themselves will be torn apart because gravity can't even hold them together any longer. And now those atoms themselves will be destroyed about 10 to the minus 19th seconds before the end. And at that time, even space-time itself gets completely ripped apart. So not a real pleasant scenario, but that's the implication of the accelerating expansion of the universe. Or at the other extreme, we might have the situation where the universe is expanding indefinitely, and we have right now a horizon of about 46 billion light years, which is the observable universe. And as the universe continues to expand, even the closest galaxies start getting far enough away from us that we can't see them anymore. The light takes too long for us to get there. So this is, potentially this could go on for 100 trillion years, with the universe getting bigger and bigger, and eventually, matter itself starts to break down because neutrons are not stable, for example. What we probably end up happening is we have what somebody described as a brief second of light, which is where we live right now, followed by this immense period of trillions of years where there's no light at all, and everything is basically just black holes and an expanding universe. The other scenario, also that I remember when I was a kid, we talked about the universe expanding forever, the universe reaching a point where maybe there was enough matter in it to cause it to contract gravitationally, and then it would start collapsing again and form another Big Bang. That was a real popular scenario back in the 60s and 70s, and we weren't sure, because of our uncertainties in measurement, whether we were going to be expanding or contracting. And we're pretty sure now that there's not enough matter to cause that kind of contraction to happen. One of the other hypotheses about the universe is it flat? Meaning, if you started walking somehow across the universe, would you just keep going forever? Or is it curved? If you started going across the universe, would you reach some point where you come back around and you get back to where you started? And we don't know the answer to that question either. So one other thing to contemplate for how things might end is as a result of us learning about the Higgs boson, which was discovered in the CERN reactor, which was first found in the CERN reactor in the last decade. And we'll talk a little bit about what we call vacuum decay. And so there are different types of fields, like gravitational fields, electrical fields, magnetic fields, and they like to be at the lowest energy state possible. We call that a vacuum state. And so what happens is things like to go to their lowest energy state. If they're at what we call a false vacuum, it means that they're not completely stable. Something could kick them off to get them down into the true vacuum state. And so what does that actually look like? So, is the Higgs field, the question is the Higgs field in a true vacuum state or a false vacuum state? And again, this is one of those things that we have measurements that indicate it could be one way or the other, and we're not 100% sure. So what's the implication of that? So here's me and my wife. Hi, Jane, I see you back there. Here we are in Rocky Mountain National Park, and we're sitting very comfortably on a nice rock ledge, and you can see the nice valley behind us. We're in a very stable position here, but we're not at the lowest energy state. If a big gust of wind comes along, or a flood happens, or a rock slide, we get knocked down into the valley here. We've gone from our higher energy state to a lower energy state, somewhere down there in that valley, and eventually hitting our lowest energy when we get down to sea level. So that's what happens when you transition from a high energy state to a low energy state. It's kind of like this immediate fall from one state to another. The problem with the Higgs field, or what some people are concerned about with the Higgs field, is there's this phenomenon called quantum tunneling. And this is basically, it's hypothetically possible for a particle of matter to disappear from one place and reappear in another place. It could go through, an electron could go through a sheet of lead. Most of the time, the lead will stop the electron, but it could kind of what we call quantum tunnel from one state to another. So likewise, something could happen to cause the Higgs field where it is right now, the Higgs particles, to go from the false state to a true energy state. And if that happened, what would happen is that not only would that the Higgs boson creates the property of mass. And so if something happens with how the property of mass works, the rules of physics go away as we know them right now, or at least the way that the universe is constructed goes away. So what happens if the Higgs boson tunnels to this low energy state?
This energy pushes the space around it over the barrier, which releases more potential energy. A sphere of the new stable Higgs field, or true vacuum, grows at the speed of light in all directions. Imagine it like setting a sea of gasoline, the size of the universe, on fire. The sphere is surrounded by a shell of energy that devours everything it comes into contact with. Whatever it touches is eliminated from existence. The bubble will continue to grow forever, deleting the universe on its way.
That's a very pleasant scenario, isn't it? Yeah. So actually, when I remember hearing some worries that people had that the CERN reactor was going to create a black hole and cause everything in the Earth to fall into it. I think what the concern was that somehow the CERN reactor would cause a Higgs boson to go into its low energy state and then start this thing. The good news is that if it happened, we would never know about it. The Earth would be gone in less than a half a second. So, but this is a possibility, and I've read a number of papers about that. Again, probably not something we need to worry about, but it is something until we learn a little bit more about how the universe works, this is another possibility for the end of things for us. Or there's another possibility for the end of things, and this is Ragnarok. This sets out in a series of signs that ultimately defines the end of times. The first sign is the Fimbulvetur, which is a long and continuous cold winter with constant snow that will last for a year. Then a red rooster called Fjalar will warn the giants that Ragnarok has begun. A second rooster will warn them all the dead that Ragnarok has begun. And finally, a third red rooster called Gulunkambi, a rooster that lives in Valhalla, a majestic hall located in Asgard, will warn the gods about the beginning of the end. So whatever our fate is, I'm pretty sure it's not going to happen in our lifetimes or our children's lifetimes or our grandchildren's lifetimes. And so what are we left with? All we can really do now is to look up in the sky and ask ourselves the same questions that people have been asking themselves ever since we could put our thoughts into words. Where did we come from? What's out there? Where are we going? We live in an age where we're able to answer more and more of these questions, but each answer inevitably leads to more questions, frustratingly, but interestingly, and that's what keeps me excited every day. So that's the end of my talk about the history and fate of the universe. And again, I wanted to extend an invitation to you for a very special place we have here on the Viking Jupiter. We are one of two ships that Viking has, the Viking Jupiter and the Viking Orion, that have a explorer's dome, which is a planetarium on board. And so that's located on deck 8 above the explorer's lounge. And you can, we have a number of, there are several 3D shows, and there's also another show about the aurora, which are movies. And then also I do a talk up there called The Sky Above Us, which is about a 15-minute show about what we might see in the night sky if we have a nice clear night. And so you can sign up for these shows at the guest services desk. I've got 2 this afternoon. I've got one at 5:30 and I've got one at 6 o'clock. We only have about 20 to 25 seats in the Explorer's Dome. So if you're interested in going, we have a couple people who already signed up. If you're interested in going, we're not going to make you sign up for it this afternoon. It'll be kind of first come, first served. But I wanted to let you know that I'll be doing 5 shows on our C day. So if you don't get a chance to see it today, if you want to take a break in packing on our C day, sign up at guest services and I'd be glad to explain what's in the sky overhead tonight. So thank you all for coming today, and I'll look forward to seeing you around the ship. And please let me know if you have any questions about where we're going. Okay, bye.